Okay, so let's continue our discussion of congruences. We have already proved that result where we saw the elementary properties of congruences. Now, one of the parts says this: if A is congruent to B mod n, then AC is congruent to BC mod n, where of course A, B and C and n are integers and n is a positive integer. But the converse of this implication is not in general true. An example showing that is this: 2 times 4 is congruent to 2 times 1 mod 6, because this side is 8 and this side is 2, and the difference of 8 and 2 is 6, so of course 6 is divisible by 6. However, you cannot cancel 2 from both sides and write 4 is congruent to 1 mod 6, because 4 is not congruent to 1 mod 6. Their difference, which is 3, is not divisible by 6. So, in spite of having this, we do not have this. We don't have this. That is, 4 is not congruent to 1 or incongruent to 1 mod 6. But under some extra restrictions, can this happen? Can the converse be true? So, we are now next going to investigate that. So, in that direction, we have this result. Theorem 4.3. So, what it states is this: if CA is congruent to CB modulo n, then A is congruent to B mod n divided by D, where, so in this new congruence, the modulus itself has changed from n to n over D, where D is the greatest common divisor of C and n. And of course, as usual, A, B, C, n, these are all integers and n is a positive integer. So let us now see the proof of this. Since CA is congruent to CB mod n, we have, so that means what? This means that CA minus CB is divisible by n, or in other words, CA minus CB is a multiple of n. But CA minus CB is C times A minus B. So that is some multiple of n for some integer k. It is a little cumbersome to keep writing for some integer k and those things. So instead, let's use notations from set theory. Let's write like this: for some k belonging to Z, where this denotes the set of integers. Alright, now what else are we given? We are also given that D is the GCD of C and N. Since D is the GCD of C and N, in particular, what does that mean? D being the greatest common divisor of C and N, after all, is also a common divisor. That means D divides both C and N. So both C and N are going to be multiples of D. So that's why we have, say C is dr and n is ds for some integers r and s. Okay. So what we can now do, we substitute for c and n here. And in place of c, we are going to write dr and we replace n with ds in this equation. Thus, so in place of c, we are going to write dr times a minus b is equal to kn, that means k ds. But d is non-zero. Why is d non-zero? Because d is the GCD of c and n, and GCD by definition is non-zero. In fact, it's positive. GCD of any two integers, at least one, whenever it exists, and that happens when at least one of the numbers itself is non-zero, is by definition a positive integer. Okay, so that's why we can cancel d from both sides, which implies r times a minus b is equal to ks. Alright, now this implies what? This equation itself implies that s divides r times a minus b. So s divides r times a minus b. But I am again repeating this. I have already said this before many times, but again I am repeating. Whenever you write from any such equation a divisibility relation like this, always make sure that the number by which you are dividing has to be a non-zero integer. Is s non-zero? You have to make sure that it is non-zero. Otherwise, this is meaningless. What is s? Where is s coming from? S is coming from this. Can s be 0? No. Because what is n? N is a positive integer. So s cannot possibly be 0. S in fact is, we can say something more also. S is in fact positive because n is positive and d by definition is positive. So s actually needs to be positive. Although for this relation we only need non-zeroness of s, which we have. Okay. So we now have this. However, we still need something else because we do not need r in the scene. We want to get rid of r. What to do about that? And this is where we are going to recall a previous result. When we were developing the theory of GCD, there we came across one result, and that result is this. Now, by so I will write the result number so that you can go back and see what we are using here. By corollary 1 to theorem 2.4. So what that corollary says is that if you have an equation like this involving GCD, you can of course divide both C and N by D. In fact, that's why we have been able to write these two equations. If you do so, the resulting numbers are relatively prime. In other words, from this equation, you get this. 1 is equal to GCD of C divided by D and N divided by D. It's as if you have divided both sides by D. On the left hand side you are getting 1 and on the right side you are getting those two numbers. But of course that's only for remembering the result. Actually we are not dividing by D. This is just a consequence of this equation. And that's what this corollary says. However, what is C divided by D? C divided by D is R. And N divided by D is S. So you now have this extra piece of information that not only is S dividing R times A minus B, but R and S are relatively prime. So you can use Euclid's lemma and claim that because of this, S has to actually divide A minus B. In this divisibility, S actually has nothing to do with R because it is relatively prime to R. There is no common prime between S and R. No common prime factor. So R does not take part in this divisibility. Hence, by Euclid's lemma, S is dividing, right? S divides A minus B, or A is congruent to B mod S. But again, never take anything for granted or lightly. Whenever you write a congruence like this, you always have to make sure that the modulus is a positive integer. Remember, just now we said that in S is non-zero, but that time we actually noticed that S is positive, and that's why we can write this. Okay. So we now have this. But in fact we can rewrite this in the form which is there in the statement. So what is S? S is N divided by D. So this is what we wanted to show. So that is our proof. Okay, so we can cancel C from both sides of a congruence if it is present on both sides, but then the modulus itself changes. Now this result has a natural corollary, which is this. There is another one, so this is corollary 1. And it says this: if CA is congruent to CB mod N, and C and N are relatively prime, that is, their GCD is 1, then A is congruent to B mod N. There is in fact no need to write a separate proof for this also. Why? Because you just apply the previous result. The GCD of C and N being 1 here means what? D is 1. So when you write this congruence, you have N divided by 1 here. So that is just N. So in this special case, you can in fact cancel C from both sides, and that too without changing the modulus. So you keep the modulus, you keep everything else, only C vanishes. It's as if you are having an ordinary equation like this, and the usual condition that C is not equal to 0, and then you have the cancellation law that A is equal to B. This is the congruence version of this corollary 1. But there is another corollary also. And this is corollary 2. It also starts just like corollary 1, but Here there is something else, a little different. If CA is congruent to CB mod P, this time the modulus is a prime number, where P is a prime number such that P does not divide C, then A is congruent to B mod P. The condition that GCD of C and N is 1 here would be needed here also, but now in place of N we have P, and in place of this condition we have P not dividing C. Does it mean that it automatically P and C are relatively prime? Yes. So here just we can write that little reason. Since P is prime and P does not divide C, we have GCD of, this is really not how we should write, but okay, let me just not write anything here. If some such problem arises now regarding space, say you have to write half of your notation here and half in the other line, it's better to write that in the new line centrally, okay, just like you write equations. We have GCD of C and P, or P and C, in any order you can write, equal to 1. So, by corollary 1, you have A congruent to B mod P. We have once discussed about how this follows from this. However, let us see once more. You just think of the GCD of two numbers simply, okay, without being too formal or without following the definition rigorously. You just think about it. What is GCD? You have two integers. What you do, you collect their positive common divisors. That means those positive integers which divide both the numbers. And the GCD is the greatest among them. Okay, because GCD, greatest common divisor. Now, what are the positive common divisors of P? Obviously, only 1 and P. Okay, so these are the positive common divisors of P. Now, we don't really know all the positive common divisors of C, because C is just some integer. At least we know that there are these two. Oh, and one more thing, C itself may be negative also. So we cannot just simply take C here, take absolute value of C. But besides these two, there may be more also. However, we do not really need to know this set fully. Why? Because we want common divisors only, no? So whatever common divisors these two numbers may have must be these two only, or maybe not both of them. And in fact, in this case, P itself cannot be a common divisor. P, of course, is dividing P, but P is not dividing C, that is given. That means 1 is the only common divisor which is positive. So automatically it is also the greatest common divisor. That's why we have 1 here. Okay. So that's how we have this second corollary as well. Okay, let us now see an example illustrating these things. What I have written here now in general may still be false because C may be 0 also. In that case I cannot take this here because I was considering only positive integers. But in that case also it does not matter because in any case 1 is always there, right? That's why. Next, we see this example. So here we have this thing. Consider the congruence 33 is congruent to 15. What is the modulus? 9. What is the difference between 33 and 15? 18. And 18 is divisible by 9, so that means this congruence is correct, it's true. i.e., but you can of course rewrite it like this. 3 times 11 is congruent to 3 times 5 mod 9. Alright, so now in order to apply, so here we are going to apply our original theorem, the one with which we started our discussion today. So you have to take the GCD of 3 and 9. Since the greatest common divisor of 3 and 9 is 3, it follows from theorem 4.2 we did, 4.3. It follows from theorem 4.3 that 11 is congruent to 5, but what is the modulus? The modulus is the previous modulus divided by the GCD. That means 9 divided by 3 or 3, which is 3. That's because the difference is 6 and 6 is divisible by 3. So this congruence is also okay. Let's see another one. Next, consider this congruence. Minus 35 is congruent to 45 mod. What is the modulus here? 8, okay. The difference between 45 and minus 35 is 80, and 80 is divisible by 8, of course. That is, so here also we can write both sides are divisible by what? 5. 5 times minus 7 is congruent to 5 times 9. Since, alright, so this time the GCD of the modulus 8 and 5 is actually 1. it follows from corollary 1 that, so we get to cancel 5 from both sides and the modulus also does not change. Minus 7 is congruent to 9 modulo 8. And the difference between 9 and minus 7 is 16, which is divisible by 8. Okay, now congruences have a property which is not seen in ordinary calculations involving integers, ordinary equations. For example, four times 3 is congruent to 0 mod 12, although none of the individual integers is congruent to 0 mod 12. That is, 4 is incongruent to 0 mod 12 and 3 is also incongruent to 0 mod 12. Or in a sense, you can multiply two non-zero integers from the, in a sense means in the sense of modulo 12 calculation. You can multiply the non-zero integer 4 and the non-zero integer 3 but still get the zero integer. Although I probably should not say like this, but in a sense you can think of this congruence as an equation. And when you really forcefully consider a system in which this congruence becomes an equation, so there you get this kind of strange things that although 4 is not equal to 0 and 3 is not equal to 0, but 4 times 3 is equal to 0. I am talking about this group. If you are unfamiliar with group from abstract algebra, just ignore this part, okay? I already have made a remark. I said that every now and then while going through these things about congruences, I will draw the parallel between number theory and algebra. So here I am drawing one such thing. When you are considering congruences modulo 12 and seeing things like this, some things are congruent to others, some things are not congruent to others, simultaneously you are actually also thinking of calculations in this group. In a sense, these two calculations are the same, okay? Considering congruences modulo 12 and considering ordinary equations in this group are one and the same. And this group in fact is a ring if you consider multiplication also. Just like the ordinary set of integers is a ring. And there are one or two such things more here. So let me just simply write them and then this section itself will be over. If AB is congruent to 0 mod n and GCD of A and n is 1, then by corollary 1, because this side you can interpret as A times 0. So you will get B congruent to 0 mod n. And in particular, if your modulus is a prime number, if n is equal to p, a prime number, then AB is congruent to 0 mod p if and only if either A is congruent to 0 mod p or B is congruent to 0 mod p, or both A and B are individually congruent to 0 mod p. The algebra version of this thing it looks like this. In the ring ZP, just like you have that ring, AB is equal to 0 if and only if A is 0 or B is 0. So unlike that ring, this ring behaves like how ordinary integers or real numbers behave. In this ring, you cannot have non-zero elements whose product is 0. Okay, this is in fact a field. But these remarks, of course, if you are unfamiliar with this part of algebra, just ignore them. And before this section, actually there is nothing else in this section, but before I end this section, let me go back to something from the beginning of the section. Do you remember that we, not us, but the author made some remarks about complete system of residues? So at the time of discussing those things, we said that we could prove those things, but we did not do so because we did not have the tools using which we can nicely prove those remarks, that those remarks are true. So now we have the tools because we now have the basic properties of congruences. However, I am not going to prove those remarks here itself in the video. Instead, after this we will start solving the exercises that we have at the end of this section. So there I will prove those remarks as well. So with this, let me just end this video tonight. So next Monday we will start solving exercises. But anyway, that's just it. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.